problems that was related to the setup. We fixed that, so maybe that helps to grow the internet, but we don't know yet. But we're trying to fix what was going on down in the room. In the meantime, the next presentation will be producing high-resolution images from low-resolution embedded cameras. Again, give me a couple of minutes before. Go ahead. You can come closer. But don't start until I get the flag that we are ready. Very good to go. Thank you.
Good afternoon, everyone. My name is Antonio Velasquez. My partner of this project was Giovanni Soto, and the professor that worked with us is Dr. Manuel A. Jimenez. Introduction. Image stitching consists of taking multiple images and overlapping crayon over each other to stitch them together, creating a higher resolution image. By implementing one of these algorithms in a best system makes it possible to get high resolution image from low resolution camera, which is low cost alternative to high end camera.
The stitching process consists of 5 different algorithms inside of it, which start with the feature detection, which identifies reference points between the images. All of the images that get inputted get different key points, which is what those reference points are called. After that is run, the feature matchers algorithm comes up, and it matches those key points that were detected between the pictures. After that, we have the homography estimation, and that's going to identify the regions where the image has to be modified so everything is aligned at the end of the stitching. The warping consists of aligning all of the errors in the region of pixels. It's going to take those key points after they are matched, and it's going to align them together so everything is seamless in the image. And finally, the blending, which consists of stitching the 2 images together.
The objective of this presentation was making stitching algorithm in 2D for embedded system. Another objective was alternate between different feature measure and feature algorithms and to measure the runtime, memory uses, and quality image. And finally, the final objective was to find the best feature detection and feature measure algorithm combination for the algorithm.
So this is the methodology that we followed for our project. We took 3 X picture image sets. The amount of pictures is set at X because it doesn't really matter how many images we input into the algorithm unless we are trying to achieve a specific resolution. We also made 3 replicas for each variation, and then we calculated the average of these numbers to consider the results valid. The control group we used was the OpenCV Stitcher class. OpenCV is an open source computer vision library, and it has a Stitcher class that has everything included, so the stitching is done seamless. The factors to switch, we chose the feature detectors and the feature matchers because this is the part of the stitching algorithm that actually processes the images, and then basically this is the heart of the algorithm. So we chose the SIFT, which is the scale invariant feature transform, RISC, which is binary robust invariant scalable key points, and ORB, which is oriented fast and rotated brief. The feature matchers that we chose were the best of two matcher and the affine matcher. These two are inside the OpenCV class, and we just altered our code. We altered our code so it would run with those. The parameters of interest to consider which is the most efficient one are the runtime, memory, and image quality. These are the results of one set of images that we analyzed, and we have the run speed with seconds and the memory in megabytes. The best outcomes in this scenario were the SIFT best of two combination, which had the lower memory cost, and the ORB best of two is the one that follows at less time and less memory consumption. But it does come at a little bit higher consumption rate. Here, you can see some of the outputs that we gathered from some of the algorithms. We have the OpenCV Stitcher class, which is our control group. And as you can see, there's the reference point in the image is the golf cart that appears at the right side of the image. As you can see in the SIFT affine and the SIFT best of two, that part is not included in the image because the algorithm did not find the key points to match that part of the algorithm of the image. In this case, we have the variations between the feature matchers, and we can see that the ORB feature detector, which with the affine feature matcher, revealed a little bit more of the golf cart, but the ORB best of two combination did not reveal the whole golf cart, which in these images you can explicitly see how the algorithm alters the output image that we have.
For the conclusion, the work we complete this semester, first we deploy and are going to stitch image in 2 dimensions using OpenCV. Then we evaluate the 3 different feature detection algorithms, SIFT, RISC, and ORB. And we evaluate the 2 different feature matchers, best of 2 and affine. And we deploy a full factorial design to do this experiment. Finally, we evaluate the 3 different variables, memory usage, speed, and image quality. Our findings so far was the combination SIFT and best of 2 provide the best memory usage and runtime speed. This option, however, provided poor image quality. The next best option found was ORB and best of 2 at higher expensive in memory usage. The OpenCV Stitcher class provides the best image output at higher expensive in memory usage. For future additional evaluation are still in process. For future work, we are creating and progressing image quality assessment algorithm to measuring the equidistant distance between key points and to completing the visual image inspection. And our future work was programming a mechanical system to automate the image capture process. This speeded up the image capture and minimizing errors in the overlapping alignment of the set of the image. Finally, we deployed the algorithm implementation in embedded system using a TBAC or similar platform and merging image and capture and stitching process. Thank you for your attention. Any questions?
Yeah. During the process of taking the pictures, did you follow a specific methodology, or did you find, like, for example, which method to take the pictures works best for each of the algorithms?
Yeah, that's a good question. When we were taking the pictures, we were using a tripod with a camera mounted on it. The way that we did it was practically visually. We were taking the tripod, so we had the horizontal angle of the camera perfect, so it wasn't moving around. And we were estimating the overlapping percentage that we needed for the pictures with using the display of the camera. So when we were taking the pictures, we were taking an array of pictures it's called like a snake algorithm. We were going from the bottom, then from the top, then we went to the middle, then to the bottom when we were taking the set of pictures. And it doesn't really matter how we input the images inside of the algorithm. So the images are not necessarily meant to be in a specific order for the algorithm to work, because the way the algorithm works is that it takes the images, and if it doesn't find any key points to match, it just goes to the other one, and it keeps going around until every image is or either discard it or integrate it into the output of the image. So that's basically the methodology that we took into consideration taking the pictures.
Does the program or does the OpenCV require that horizontal alignment to be just right, to be perfect, or if you have two images that are slightly offset with like a rotational difference, is that something that the program also identifies features and corrects?
Yeah, so the algorithm, it doesn't matter if they are aligned or not. We're just basically facilitating the algorithm to do the best work possible. But that's what the warping and the blending is for, because when the images are the key points are matched, the estimated homography that we talked about, it estimates where the image needs to be modified so the image is aligned. So the warping is done in a spherical plane, and then that is it's flattened, so everything is the best alignment possible.
Thank you.
Any more questions?
And the algorithms that you use, that you're actually using to do image stitching could be like a way to provide the depth and be able to create 3D images at the end?
That is a very good question. Now, at the time, we haven't really evaluated a 3D environment, like doing different algorithms to depth and and increase the depth of the image. But there are studies involving OpenCV that they actually use it for that. But for the scope of our project, we haven't considered that yet.
Do you expect brightness of the picture that you're taking affect the performance of your different algorithms?
Yes. So when we were taking the first set of images, this was not the first set of images that we took. We had a problem with the camera where it was oversaturated, and the algorithm tries to correct for that. The algorithm, if there's a lot of light, it tries to either brighten up the whole picture or try to damp the brightness down. So the algorithm, that is something that at the time, the algorithm does not correct per se, but we are trying to take the picture with less light and exposure as possible, so the output is the best that it can be. No more questions? Well, thank you for your attention.
Our next presenters are Victor Morales, Sidney Serrano, and Melody Cosme in bidirectional converter.
Testing, 1, 2, 3, perfect, okay. Good afternoon, my name is Victor Morales. Let's see, nope, okay, how about this? Okay, let's continue. My name is Victor Morales. With me, I have my partners, Sidney Serrano and Melody Cosme, and together we're going to present to you the project regarding the bidirectional converter and how we work on it, and how that relates to the Tapstone project we additionally worked on utilizing that design. Basically, the overview of the project is that the customer needs a bidirectional converter that is compact and easy to manipulate so that it can be used in future class demonstrations seamlessly. By seamlessly, we refer to that the bidirectional nature of this converter is automatic and not segmented, not that you have to actually switch on or off that nature particularly. This bidirectional converter must be able to rectify AC voltage into DC so it can feed into the customer's microgrid or inverse the DC voltage into AC. Basically, this would mean utilizing a simple electrical outlet, connecting that into the converter, and then from the converter into the customer's microgrid. Regarding the objectives of the project, obviously we need it to be bidirectional, have a suggested power rating between 400 and 500 watts, a PCB design if possible, and have it operate in 2 quadrants. By that we mean that the voltage is maintained positive, but the current can be negative or positive. An accessible user interface, which would mean that dials, displays for the customer or anyone that is going to operate the device, so that they can understand the device itself and operate it without any problem. It to be modular, as lightweight as possible, and have an aluminum box or non-conductive enclosure. We mentioned that because if it is an aluminum box, we're prioritizing the sturdiness and the protection of the box itself and the components. But if it is a non-conductive enclosure, it would be, non-conductive, so it would lessen the possibility of any arc or sound possible for the device. Regarding the project deliverables, we have design specifications, which would be the circuit parameters, what it's operating at, what suggested voltage we're going to be utilizing, be it from 0 to 12, 12 to 24, and converting that to 48 volts. The simulating schematic and simulation, which would require us to create a prototype and then utilize that prototype, simulate it, and transition that into a physical prototype. Then that would transition into the prototype build itself, which would be a more experimental process. The performance testing and results, which would allow us to extract data and utilize that data to actually compare it to what we expect the converter itself to operate at and assure that it's operating correctly. The final build itself and the applicable code compliance documentation, which would assure us that what we're doing and designing is viable and actually acceptable within the national electrical codes and various other documentations regarding electrical codes.
Okay, so in terms of a CAS1 project, you have to come up with 3 solutions, and then after that, you have to do some type of decision matrix that objectively gives you the best outcome going forward. So now I'll be talking about that. Like Victor said, we're working with a bidirectional converter. Originally, we looked into working with a single-phase bidirectional converter. So as you can see here, is a relatively simple design for IGBTs, and with that, we could achieve what we were going for. From there, we also consider a resonant dual active bridge converter, which is a little bit more complex. As you can see, it has like 14 IGBTs, but kind of the biggest thing for us working with this was that we were going to have to work with that inverter, with a transformer in the middle of the system itself. And then after that, we also looked into working with a NPC or a neutral point clamp converter, which originally was what we really wanted to go forward with because we had a lot of information regarding this type of converter. But we quickly realized that for this converter, you have 6 switches, and synchronizing them to not be in the same state, meaning on or off, was pretty hard. And the importance of that is that if you have the switches that, like, when it's supposed to be on, it's off, or something like that, it makes the system completely unstable. And obviously, we don't want that for our customer when it's using the system in future classes or demonstrations.
So the way that we decide which one of these topologies we're going to use for our project, we use and develop a decision matrix. In that decision matrix, we evaluate 7 different parameters. Some of them, fewer modifications, information available about that topology, a simpler design, TRL, lower cost, and user-friendly. The way that the weight of these parameters work was in a scale between 2 and 9 and was in percentages. And the result was the single phase at first place, MPC at second place, and DAP at third place.
And with those results, we quickly went to simulate the single-phase converter. And then, as you can see, the following simulation has both a AC input on the left side, that is, and that block on the center, which is named IGBT H bridge, we find a full bridge and various other components. And on the right side, we have various other elements and a control circuit on the lower right side. The reason we have a control circuit is that we require the converter itself to have certain PWM signals, and I will explain that a little bit later. But essentially, this is a much more simplified version of what we actually have. Much more components, and I couldn't fit that in the slide, so there you go. The following slides will then present the simulation itself and the results found within certain scopes.
So, like we originally talked about, we wanted our bidirectionality to be seamlessly. We didn't want it to be manual. So we opted out for achieving bidirectionality by controlling voltage. So here in Simulink, you can see some simulations where by making our voltage higher, we were actually discharging our battery, which is what we were looking for. And then from there, we can do the same thing, but like the other way. You lower your battery voltage, and then your battery actually charges. So that's what we're seeing in these two graphs.
As I mentioned previously, that is the control circuit utilized within the single-phase converter. We have an input on the leftmost side, which would be the analog to digital input utilized from the C2000 microcontroller that we use to not only generate but also output the actual PWM signals that are seen on the rightmost side. As you can see, there is a lesser than and larger than 0 blocks, which would indicate that we have both positive and negative PWM signals. This is so that when you have the sinusoidal signal, both the PWM plus side is synchronized with the rate, with the rising of the sinusoid and the sinusoidal wave, and the negative PWM signal is coinciding with the negative or lowering of the sinusoidal wave.
So continuing on with our pictures, here is our test bench. From top to bottom, on the left, you can see in orange our 12-volt test battery, which was what we were charging and discharging. We had a multimeter hooked up to that, in reality more of an amp meter, so that way we could confirm that we were seeing the negative or the positive current going in or out of the system. In green, you'll see our bidirectional converter, which was the system that we opted for, so it's the single-phase bidirectional converter. In blue on top, it's a red device. It's a variable transformer. With that, we were manipulating how much AC we're putting into our bidirectional converter. And then we had in red our C2000 controller module, which is a TI system which is what Victor was programming and showing. And then we have the three smaller circles, which is purple, gray, and yellow. So we have a voltage sensor to make sure that the PWM and the AC were in phase, so we could measure that with that. And then the 12-volt battery was for that sensor, and we had a regulator from 12 volt to 5 volts to be able to excite the sensor.
In terms of the converter, the converter has a integrate microcontroller in a card that were not compatible with our system. So what we did, we developed a new card for that converter, and we designed from scratch the card, and we did the design in Eagle. Your left image is the design that we developed as a team, and the right is the image of the card after manufacturing process. With this card, we have the information that we want to need, like PWM, pulse, BCM, DC, and BDC sense, and also we use that for the C2000 microcontroller information.
So going back to the results, one of our highest things that we really wanted to look forward to was being able to have a PWM positive and negative that was in phase. This was very important because, like I said previously, if this wasn't happening, then our system was going to be completely unstable. So in the right picture, you can see the simulation of what we had already shown, and that's what we were expecting. And then on the left, you can see an actual picture of our oscilloscope when we were experimenting with the system, meaning that we were doing Good. So here, same picture, but with the negative side. Simulation is in the right, and we can see that the blue lines are in phase with the lower sides of the AC, and then in the left side you can see the experimental picture, which is showing the same thing. And now we have some small, like very short videos of where you can see the battery actually charging and discharging. So in the first picture, the battery is actually charging, and I don't know if you can see it in this screen, but if you were able to see the amp meter, you could see that it has a steady number until we start manipulating the variable transformer, so you can see that it's charging or that it's charging at a higher rate. And then the second video is actually of the battery discharging, so there's a negative number in the amp meter, so we know that the system is working the other way.
So in summary, we evaluate 3 different alternatives for our design, and we select the single-phase bidirectional converter as the final design. We develop simulated models for the converters and controller, and to engage the bidirectional ability. So when is high DC in the side voltage of high DC, the power flows from DC to AC, and in the side of the low DC, the power flow from DC to AC. Develop and test the C2000 base control, synchronized to AC signals, and develop the prototype. And the next steps are further testings, and we are going to provide to our customer the PCB design for the final result. So thank you. Any question?
Yes. In your objective, you had set up certain criteria. How did you come up with the criteria? And end of the day, when you finish your prototype, which one did you able to match?
Well, okay, so the objectives were decided between the customer and us as a team. The bidirectionals is completely. The PCB was, if possible, but we are currently working on. The power rating also. The operating into programs were completely. The lightweight weight as possible compared to the customer currently microgrid. And the accessible user phase. So what is next is the part of modular when the PCB design is complete.
My question is, when you design the entire system, did you consider the charging rate that the battery can handle, or you just assuming that your charging rate is so little that it doesn't matter the battery charging rate limit?
What rate? The current.
The current charging rate for the battery.
So your question is, if we consider how fast we could charge the battery?
Yeah, because the battery, all batteries have a physical limit. They have more charging rate. If not, the battery can be damaged. Do you take that into consideration, or just assume that you're charging very slowly on the
Yeah, I mean, we're not necessarily, okay, I understand what you're saying, so we look into the battery data sheet, so we understand the limits of the battery, if that's your question, yes.
And that is taking into consideration on the design, like you can change like a parameter of the design to a different battery, or
Yeah, so you can manipulate, like I was saying, the battery discharge or charge current by manipulating the variable transformer that we had. Yeah.
that means that you can, when you connect it to an AC
like a power source, the AC needs to be controlled. That means that you cannot connect like an infinite power source, like for example.
We don't have an infinite power source. Correct.
I saw two voltages there, 14 and 24, something like that.
In the battery discharge in, yeah. This?
Yes.
Yeah, so like we were saying, we manipulate bidirectionality by with voltage. So you have to up your voltage of your battery to be able to discharge it, and then lower the battery voltage to charge it.
Well, the battery has a fixed voltage that it goes around a small area. Which is the battery is for 12 volt, 12, 14, how much is the battery?
It's a 12 volt battery, yeah.
How much is the battery, 12 volt?
Yes.
And you put in 24?
No, so this is just a simulation so that we could understand that the system was working in the simulation.
Okay, so that's not the actual battery.
This is not experimental, yes. This
Okay,
is a simulation. Yeah.
So, for you to be able to charge the battery, you have to have an extra source that take care of the load will charge the battery.
Yes.
Okay, which is that source? The grid?
Yes. The plan here is to connect to a DC microgrid.
So you have a microgrid that will take the extra charge from someplace else and put it into your battery.
Correct.
And the battery will, at some point, will.
So our battery is acting. We're using the battery as an example of our DC microgrid. What we're designing here is a bidirectional converter that can work between the utility and a DC microgrid.
So I'm trying to understand how your converter decide when to switch to one direction to the other.
Okay, so the design is for our customer microgrid. That design has two different inputs and has one from low DC and the other one is high DC. So when you use the high DC, the power flows from DC to AC. And when you use the lower part of the lower side of DC, the power flows automatically to AC to DC. So that is, we are controlling the DC areas in the microgrid and the higher one and the lower one, and automatically it's going to make the change of the direction. I don't know if I completely answered the question.
That's okay, we can discuss it later. Thank you. Very good job. The next group is a big group, but there is a small representation of them here. Rum Marino, you probably heard about them from last year. They didn't include the name of the student because there are so many, but you can tell the numbers.
Right. Well, good afternoon. Welcome. My name is Ordep Agustin. I am the team captain of Rum Marino. Right here, I am joined by
Victor Rifkol.
Diego is one of our embedded systems, software architecture, and computer vision members. He's working in all those divisions with us. And then Victor over here is our electrical systems leader. So just to get a quick little rundown of who we are and a little of our agenda, I'll be talking a little bit about the history of Rum Marino, some general updates we've been taking care of, some division updates, and then some questions that you guys might have for us. So our evolution, this started as one small prototype with Proteus right there. It went from just some PVC pipes, a suitcase with some pipes there just to keep it afloat, to making headlines in El Índice newspaper, and then it evolved into Proteus 2.0, and then 3.0, which is the final Proteus model that competed in a couple of competitions, 2016, 17, 18, I believe, and then I think they also went to the online version of the competition. And then right now we're working on Hydras, which is a bigger model of the submarine. It's capable of a lot more things. It has more space for different items like a camera, some servos, a gripper, and all that type of things. And then over here, I think we're missing some pictures, but it's all right. The competitions that we go to are the RoboSub Nation ones. They are being held in San Diego, California. That is one of the pictures from 2017 from all the teams and the staff that took care of that event. And then just to run a little bit over this, some general updates. We took our software team and we renamed it into computer systems because there was a little bit of confusion of what we did in that division. A lot of people thought we were just working with just strictly software things, but we also have different stuff like embedded systems, computers, stuff like that. So we just brought in our spectrum a bit and not have it so narrowed down to software. We changed it like that, and then we reorganized our structure. So we have a new breakdown structure, and then we also created the sonar system task, which is their whole division. So they take care of everything dedicated to sonar, signal processing, and location of it. We also received and also registered into RoboSub 2023. So we are planned to go to compete this summer on July 31st to August 6th is the competition. So hopefully you'll see a lot of pictures of us there. We also joined the IEEE RAS, which is Robotics and Automation Society, and the Control System Society. Currently, I am the vice president of those branches. So a lot of cool things coming next semester, just a heads up. So over here, just the divisions of the breakdown that I mentioned. So here we have myself, project manager, my co-manager, which is the ex-captain of the team, Osvaldo Aquino, and then we're breaking down into three main branches, which is hardware. Then we have computer system, run by Osvaldo and I. Hardware is being run by Joshua. Also management being run by Linda Marin. Then in hardware, it breaks down into mechanical structures and electrical system. Paula Guzman takes care of the mechanical side of things. Victor over here takes care of the electrical side. Then computer system, as you can see, we're just not software, so that's why I decided to rename the division. So we have control systems, software architecture, sonar systems, computer vision, and embedded systems. So you can see why there's a little bit of confusion just calling it software. So control systems being run by Kevin Colon. He is currently doing his capstone, so he couldn't be here. Software architecture is being run by Jomar Perez. He is currently in a co-op with Naval Nuclear Laboratory, so that's why he couldn't be here also. Jesse Torre runs sonar system. He's also doing his capstone, so he can't be here. And then computer vision, myself, I'm taking care of that. Embedded system, Osvaldo Aquino. He's currently in the pool, getting wet, testing the submarine, all his embedded stuff, so he's not here as also. Business-wise, we got Frances. She's doing her final presentation, so she's going to be here sadly. And then operations, Kevin Diaz. He had a dentist appointments. That's like the lamest one. So he's taking care of that. Everyone here, that's basically the leaders, and then each division has their respective amount of members. We're currently around 35 members total, ranging from all those different teams. So just to get started a little bit on hardware, the stuff we've done, just what we've managed to complete. Last semester we had some problems with our seal. We finally fixed that. We got the O-rings properly installed. Our seal is 100% waterproof. We made a new Hydras 3D model so we can use it for the URDF for control systems, which I'll talk a little bit later. They're also working on a torpedo launch system for the one of the tasks in RoboSub that I'll get to in a little bit after I'm done talking about other divisions. We've also basically made a gate similar to the ones that are in the competition with the dimensions, the colors, and all that, so we can simulate the tasks that we'll be doing during the competition. And then we're also going to recreate different objects like different posters, objects that we have to lift off the ground and transport them with the gripper, stuff like that. So I'll just pass it over real quick to Victor so he can talk a little bit more about electrical systems.
Hi guys. Well, in the electrical systems division, we are going to be talking about our power systems, our cable management, PCB redesign and research, camera rewiring, and the updated hardware block diagram. So our power systems is practically divided in three phases: 24 volts, 12 volts, and 5 volts. Thank you, Adep. In the 24-volt phase, we have that the thrusters and the Jetson. Thrusters and the DVL are or draw power from this voltage. In the 12-volt phase, we have the Jetson, the microcontroller, and the and the AMU. And then with the 5-volt, we have the camera, the Pi. So that's practically how it's divided our power systems. So going a little bit more back, and that's the updated block diagram. So our cable management, since it's a lot of wiring, right? So we had to have a way to keep tabs of where everything connects in the submarine. So we taped some numbers in order to have a better notion and from where everything connects. So that way we just like guarantee we have every connection right and not mess up and make a costly mistake. So the camera rewiring with the set camera that the submarine uses, we had a little bit of trouble because the USB didn't fit through the hole in the hydrous. So we had to cut the wire and resolder it. That was a little bit of work because the cables were pretty thin, but we did it, and I believe the camera is working. So yeah. Also, we redesigned a new PCB because we have to implement the gripper and the camera. So that is something that's going to be implemented soon for the competition. And yeah, we're going to keep researching for this PCB in order to keep making it better and more optimal. So yeah, that's basically everything for electrical systems.
All right, so also over here we have the embedded systems and control systems. These two divisions I'm just going to talk interchangeably because currently they're working on similar tasks. But embedded system is more specifically working on the DVL implementation, IMU, pressure sensor, servos of the cameras, and then right there we can see like the different names: the T200 thrusters, the gripper, the Pro Micro Server for the camera, and the Blue Robotics MS5837 pressure sensor. And they're also working. But that's a little outdated. Sorry, my bad. They completed the implementation of the DVL, and it's reading all the values correctly. We're getting accurate numbers in live time. And also with the pressure sensor, we're also getting that as well. And the IMU is also being developed as well. So control systems, they basically take care of all the mathematical equations to control the different thrusters and create a type of simulation for the movement of the submarine. But due to the way that this semester we're tackling the problem, Osvaldo Aquino took the embedded systems project as his capstone. So they've had to work with a lot of those thruster mechanics as well. And they've also managed to get everything in a up-sub type of client using ROS, which is Robot Operating System, and they have all that working. I was informed that they had a successful pull test as well, so claps for them real quick. And then they're going real quick with that as well, so hopefully I'll have some more updates on that as well. But at the moment, that is what they've done. They've managed to implement all of that, get the sensors going, and they also have the rotors going. Here's one of the pictures of the equipment that we're using with the kill switch. This is the power connector. We're getting like voltage values here, the relay, and this is basically what's going to power our Jetson, which is the microprocessors that we're using. And then here, Obaldo, he had to show up somehow. So here he was testing our Jetson and the DVL. So right here we have the Jetson tied up to his monitor, and the microprocessor over here is the Pi. And right here is his DVL. He is currently calibrating it. Oh, my bad. I switched it, nice. There we go. Alright. So he's this is the DVL that he was calibrating at the moment, and then he placed it in the water and got some nice results. I don't have pictures of the results because it all happens in the terminal, and it happens way too fast to like take a picture of it properly. But we're getting accurate values, and after some calibration with the submarine and movement, we should have real-time values of velocity and how fast our submarine is going. So we're here in software architecture. I'm just going to pass it over to Diego real quick so we can talk about that.
So for software architecture, we've mostly been focused on two parts, which is setting up our state machine as well as setting up Docker to resolve our dependency help. So for our state machine, we've analyzed everything that we need to do, and we've started creating it in a way that can work for the competition. But for Docker, which is something that we've worked more this semester, we've basically begun implementing the use of a Docker network in order to containerize our entire software stack, in order so that we can have much more agile software development as well as easier development environments, so that our users can set that up more easily. And basically, we've been mostly focusing on how to get information from one Docker container, which contains a big chunk of the information. For example, computer vision. We need to be able to have a way to pass that information from computer vision and all the values that that's returning all the way over to every other container that we have in our stack. So for computer vision, we're still using the same model that we had last year. We marginally improved its performance. It's now at approximately 94% accuracy. Approximately 94% accuracy. Yeah. And our Docker container is fully operational and includes all the dependencies necessary in order to run our computer vision stack. And we've also begun the RViz implementation. And at the moment, Docker is basically done, so now all that remains is for everything to come together.
All right, and over here for the sonar system division, since they're a little bit new, they had to restructure themselves. We named just our leader, and he had to build his own little team. So we went through an interview process, got some students working on it as well, and they basically just structured themselves as an own entity within the team. They've managed to begin the software testing and manipulation to process different types of signals and get everything, and we can also simulate noise being inserted into the signal using different Python libraries. Currently, what they're doing is waiting on some hardware limitations. We found out that one of our hydrophones broke, so we had to replace it, and we're looking into a newer model that can let us access a lot more libraries that are more compatible with the other stuff that we're using in ROS. And then over here in management, operations and business have been doing different types of fundraisers, structuring ourselves with different activities, giving us a way to have a main hub for all different communications, our documentation, and we're using Microsoft Teams for that. They're also staying in touch with the different sponsors and stuff like that. And then we also had a team photo shoot. This is one of the pictures. We did an AirPod raffle, and we had a revenue of $400. We registered for RoboSub, and then for next semester, we're planning monthly pizza sales, car wash events, and stickers. So keep an eye on that. This is some of the stuff that we have sold. We bought different equipment for the team, be it USBs for storage, Wi-Fi antennas, filaments for the 3D printers, connectors, and just other stuff as well as some equipment, some goodies. This is the new camera we're also testing. Unfortunately, we can't fit it in the submarine due to hardware limitations, but a lot of the libraries are very compatible with the camera that we are using. So we're just reverse engineering how to use and access those so we can have a better model at the end of the day. And then, yeah, that's about it. I'll just wrap it up there. I would like to talk more about the competition, but if you have any questions, feel free to ask them.
So, working with similar technologies, it is a big limitation if you don't have the correct parts provider, right? So I wanted to know, because I can identify already you guys buy a lot from Blue ROV. Do you guys have other similar companies from which you can acquire similarly rated ROV products?
Well,
Have you run across some in your market research?
yeah, so a lot of the things that we buy from Blue Robotics is just because they're directly sponsored by RoboSub. So a lot of that is just since we're registering to the competition, it is that is how they keep the playing field as even as possible. So a lot of the equipment that we use is the same, but there have been different like the connectors that I showed up here and stuff like that. Like this is not RoboSub related or anything. This is just different equipment that we need to use for our design, for example. So it really just depends on the equipment that we need. But a lot of the mechanical structure stuff, like I like the cabin that we have, a lot of that technology is very similar to one of the ones you're referring, I believe. But yeah, mostly it just depends on what we need and what it is going to be used for.
Since team is pretty diverse and big, from functionality point of view, program management could be very difficult. So, what kind of challenges have you faced, and how did you overcome?
So at least for programming wise, we've had a lot of issues getting everything centralized in a like one solid GitHub because the team does have a GitHub, but that was owned by one of the previous captains of the team, and I believe like the credentials or something got corrupted and we couldn't access it for some time. But we managed to get in contact with the person. We sat down for a while, reconfigured everything, and we have access to that GitHub once again. So a lot of the code that we're using, we're just publishing it to that GitHub, have everything documented, because well, this project will continue for future generations. So we want to keep everything as documented as possible. A little thing that actually Diego is working on is different videos of how to manage our Docker container, for example, because not everyone knows Docker. That is not something that we learn here in the university. It's just a tool that we have utilized and we're utilizing for this sub. So he's just been working on that for us. What else? Well, thank you very much for your attention, guys. Have a great rest of your afternoon.
Thank you guys. Our next presentation is our radio sponsored research project, Red Cross Safe and Well Integration.
Hello everyone, my name is Omar Rodriguez and I'm here with my companions Dennis Martyr and Dylan Mendes, and today we're going to present the part, which is part Al, which is an implementation for the Well and Cost Safe and Well system. So formally we are 4 teammates, but unfortunately due to a captain part, one of our teammates is not here. So we'll be speaking specifically Dennis, me, and Dylan.
So, during 2017, we had the natural disaster of Hurricane Maria, which caused multiple infrastructures of not only electrical grids, but also communication systems to go down. So we have communities which were out of reach for not only days or weeks, even months. So there wasn't a plan of action in mind to attend those necessities at the moment. So it caused a lot of needs in reallocating resources for those communities that had no contact or communications. So afterwards, in 2018, IBM did an hour of code where a group of 5 student uh, people form up the thing called Park Out, which is a joint effort between multiple technologies using log systems and IoT devices, which we'll get right into it, where we'll have an area, let's say we have a desert, so it's since there's no communication system, we'll implement IoT devices called ducks, where we'll place them around, and using Wi-Fi signals, we will connect to the duck and say if there's a sandstorm coming, you can connect it and send basic necessities like this is danger that is imminent, this is the people I'm around, and this is what we need for combat the sandstorm. So they will communicate one another until they go to a specific duck, which we'll call the Papa duck, and it'll set to a database system where all the information for necessities are safe. So with that, we can have an idea of what are the actions and the bounds at the moment. So we have a better way to respond. So since this is an open source project, the Safe and Well, the Red Cross Safe and Well program is interested in implementing this technology into their own natural disasters and emergency system. So the idea of this is implementing the LoRa-based Park Owl system for their own program and implement it in here for their program. So the objective of this research project is to leverage the Park Owl technology to facilitate swift communications during natural disasters. It is also to develop a new user interface for the local Wi-Fi interface for the Safe and Well registration, and also have a local store and forward capability for the Papadoc for relaying the Safe and Well website. So my companion here, Dennis, will talk about the terminologies, more or less.
Thank you, Owen. Before I head into the steps we're taking to complete the project, I would like to go over some of the terminology of the project. First, we have ad hoc, which is a rapid deployment network system to establish a quick temporary local area network. After that, we have the duckling. The duckling is basically a node for the network that will serve as the first contact with the user. This is the way that the user will get access to the web app and be able to send requests to the Red Cross. Then we have Mama Duck, which is above the duckling, which it'll recompile a bunch of duckling data into organized so that it can be sent to the Papa Duck. The Papa Duck will collect information from the Mama Duck that will be sent directly to the database of the Red Cross. Now, our methodology for the project consists of first researching about UML diagrams and how they can be used to describe software development and software architecture. After that, we develop a domain and use case diagram that will be used to describe and better write down the process and software development of our project. And after that, we'll be designing a network architecture based on the ad hoc principle, as we're trying to create a mesh network that can basically work in any place in the world and be able to be accepted via any network or other mesh networks. Finally, using the cluster.doc protocol, we'll be creating the different nodes. First, we'll be developing the wireless network. After that, using the ducklings, we'll be assigning a node in the network to be ducklings, so that it can represent a user. As a user for our project is on a household level, which is around 5 users. After that, we'll be setting the mama ducks, and finally establishing a connection with the papa ducks. Aldiano, take over our results.
Some of our results include we have drafted a use case diagram for the system, which is the first picture, and a drafted domain model to illustrate the system service functionality. Also, we have obtained some spare equipment from the other Project Owl project. We have obtained some Mama ducts, some LoRa transmitters, solar panels, and batteries. Now we go to our companion one.
So as future work, since we have a lot of equipment that we received pretty recently at the end of the semester, we're gonna do an inventory of the amount of equipment that we have. I will be going over in terms of how to not only be able to use those equipment, but also have a way in order to make more of this Mama dogs, so we can start experimenting. Since we want to focus more on the scope in determining how to work with the technology and how to be familiarized with how to use it before we implement it into a more greater scale. So as for next semesters, we're gonna focus more on learning about the technology before, like on a practical approach. And additionally, we'll be developing a comprehensive documentation for encompassing the requirements and the design of the system to facilitate the clear communications and support between the various activities. And as mentioned, have a small size version of the RL system so we can familiarize with the cluster dock protocol, which is the protocol that is used with the LoRa for communicating between the different docks. So, are there any questions?
From practical point of view, do you know how the effective system going to be and can it scale?
Can you repeat again the question?
How the system gonna be? Is it system gonna? How effective it will be? You know, and can it scale? It means you know.
The effectiveness of the project itself still remains to be determined, but based on Project Owl that happened before us, it turned out to be extremely effective as there are already nodes in Puerto Rico. I believe there are around 5 Papa Dogs around the whole island. And one of the main key points of the project is that it's supposed to be scalable. That is one of the purpose why we are using ad hoc. At first, we're going to start developing around a household, which is around 5 users. But then, if the results seem to be good or even better than expected, then it will scale it up to be a community, and bit by bit, we'll go into the island and even the country.
And I'd also like to add the deployments for all the nodes in Puerto Rico. It's all available at the Park Al website. So you'll get the field reports for the deployments that they not only they've done in Puerto Rico, but also in Texas.
According to the agenda, we have a wake-up call. This is snack time. We already have the snacks over the other room. Let's come back in about 20 minutes or so, maybe. The snack time is supposed to be 30 minutes. But because I saw this is gonna be a lot of crowd, but we are so little now that probably we can do it in 20 minutes and finish early.
Bajaron acá, la verdad. ¿Cuál? ¿Este? Habla y del proyecto de cálculo. Ven, ven acá. Habla del proyecto de cálculo. Fue mi él no va nunca a terminar. Pero es que ya
¿Quieres saber? Me parece que te enviaron bien tarde la presentación donde están, te vamos a regañar. Ellos fueron los que fueron y fueron comieron Si terminamos antes, pues da tiempo de ir a ver la presentación de los otros. Su presentación es 95 minutos.
No se ve lindo.
Está bien, se ve bello, pero son 95 megas que fue bien difícil enviarse a favor.
Tuve
Y a
que...
Pedro Torres Carraquillo que tiene que estar en la tuya. Yo he dado en el pasado, si hay algún otro que necesite, el único problema es que tengo un viaje. Ya yo la tengo lista. Hay algunas que tienen material, bueno, pero son materiales sencillos. Raúl, café, agua.
Hasta que tengo que ahora sacar el template para poder la presentación. Ese es el problema, por eso es que no consigo. No, hay que sacar las palabras. Yo sé que tú eras así. ¿Te acuerdas del estudiante que yo decía que no podía hablar en inglés? Yo ahí. Carlos, ¿tú comiste, mi hermano? ¿No quieres que me lo pase a pasar? Tuve que aprender a trabajar con cantante, ¿no? Trabajo así.
Sí, estoy de acuerdo.
Tuve que hacer autenticación, nos mandaron a hacer la descarga, estoy usando, y era que tenía que hacer. Y como 5 formas de autenticar.
Sí, después de que uno tiene que ver
Vamos a tomar bebé café.
Si antes no hablaba inglés y terminé trabajando ahora ya.
Ah, yo sí. ¿Te sirvió para algo el trabajo? Allá, ¿recuerdas acá? A comer. Está buena
No las he podido ver todas porque he tenido que salir un par de veces a hablar con estudiantes, pero todo el mundo. Sí, es que no, pero me gusta. ¿Sabes cuál me gusta mucho? El chamaco graduado. No, no, yo sé, pero sorprendido y tú, o sea, porque no es solamente, o sea, una cosa es que tú tienes un nivel más fuerte. Ah, ¿verdad? Ven acá, tengo una de mira, yo estaba pensando la América algo que se me ocurrió que eso podría ser una compañía que cree que por especialmente por la venta de a todo el mundo online, el Zoom, el efecto de ir a la oficina está desaparecido. Pero tiene que funcionar. Online tiene que funcionar. Por eso yo creo que se puede dar. Porque la idea es no saber lo que es. No, no pasa más nada. Tiene que ser planta o whatever, pero entonces ya igual subir más el internet. Si tú supieras que todavía estaba pensando, y lo que pasa es que es difícil, o sea, porque no hay una solución única. Pero estaba pensando que tanto entonces no sé si eso es lo que de nuevo, de lo que he visto, por ejemplo, eso no, y hay una característica, porque me quedé hablando fuera, pero el muchacho me conoce de otra cosa, y me dijo, cacho, ahí creo que el dron, no fue el dron, ahí como a la milla de, ¿sabes? No, no, yo sé. Eso es lo que me dijeron, que era un montón de gente, alguien me lo comentó. No, no, yo sé. Ven acá, déjame preguntar. Pues si tú supieras, yo creo que fue un error en el timesheet. Te voy a decir lo que pasa exactamente. Si yo genero el documento que les pido, aunque lo generen los estudiantes, pero tienen el link, Lincoln me pide que le haga una firma para contacto con todo el proceso administrativo de que diga si esta información pública se puede sacar. Pues para evitarme eso, yo siempre lo que hago es que trabajo la propuesta con los estudiantes, pero les digo ustedes la firman, porque para efectos prácticos está bien, pero yo puedo, o sea, lo que te quiero decir es, no, pero lo puedo hacer yo, o sea, la parte logística de entrarla lo podría hacer yo. Sí, no, ya yo sé para el futuro, te lo mando por ahí. Sí. No, pero es eso que te digo, el asunto es que siempre, históricamente, yo le digo, porque yo siempre lo apuntaba por email antes. Lo que pasa es que ahorita yo tengo revisando un montón de gente y estoy con el agua, pues entonces le dije a los muchachos, les dije, no, prepárenla, pero creo que hubo una desconexión con el tipo que está ahí, con Kelly, el muchacho que está en el nombre de la propuesta, que es el otro supervisor que aparece ahí. Me da la impresión de que él nunca cayó en tiempo de que había que enviarla por email.
cuando salió que no estaba, yo dije, eso es que nunca le enviaron. Nunca pude encontrar evidencia de que la habían enviado. Quiero que la opinión tuya de por qué lo hicieron. Antes de irse muy necesidad de o de medio, whatever. Yo por mí vengo los 2 días. Aparte te iba a decir, si hay alguien que te puede sacar, pues no. Sí, señor, fíjate, lo puedo hacer mañana. A mí, yo prefiero 2 días. Yo, la, sí, lo que pasa es que yo creo que el día no se puede convertir tampoco tan largo. Yo tengo a email que yo no me lo voy a dar esta noche, pero por lo menos le mandé a manifestar. Estoy seguro que va a ser un aviso, pero es que yo hasta la semana, bueno, tuviste los videos, hasta la semana que viene yo no sabía qué pasara, yo no sabía si venía, porque todavía estaba, voy, no voy. Entonces me quitaron una reunión lunes y martes esta semana que yo podía no venir a esto, pero esa reunión no podía faltar bajo ninguna circunstancia. Entonces la quitaron, me movieron la semana que viene y dije, ok, estoy en una oficina, ya pues, entonces estoy. Pero lo que iba a decir es que yo tengo la impresión, la gente de Cyber cuando vino a la universidad, tú sabes que vinieron conmigo 2 más cuando vinimos a la feria. Y los dos, ahí lo que es totalmente Cyber, y ahí lo que es Cyber, que ahora está mezclado con ella, o sea, que cubre las 2 cosas. Tienen mucho interés, se dieron cuenta de que hay una mitad para Cyber. Entonces, estoy seguro que van a tratar de pasar por un proyecto de IAP. O sea, que a lo que voy con eso es. No, estoy de acuerdo. Pero yo siempre yo le digo, yo no tengo problema con eso. Yo no tengo problema con eso. O sea, con pasarle dinero a un profesor o algunos recursos que haya que comprar. Entiendo. Entiendo. Claro. Pero el problema a mí es que el problema es la logística. Yo lo puedo hacer, pero yo tengo que establecer un sistema. Este dinero lo paga el recurso humano. Los proyectos que yo tenga los tengo que pagar yo de mi proyecto. ¿Okay? Yo no tengo problema con eso porque yo tengo dinero por una gente de la que trabajo que me da una cantidad no muy grande, pero me da una cantidad de dinero para hacer la outreach y este y aquello. Y hago algunas cosas que son súper sofisticadas por doctorado y hago otras cosas de undergrado. O sea que yo tengo un potecito de dinero. Y 3.000 pesos es mucho, pero el problema no es ese. El problema es que para yo dar los 3.000 pesos tengo que pasar por todo el proceso administrativo de darle dinero, aunque sean 3.000 pesos. Entonces, tendríamos que empezar el proceso. Si empezamos el proceso ahora, yo sé, pero lo que te quiero decir es, si tú me dices hoy, yo digo, está bien, yo voy a necesitar 6.000 pesos, porque voy a poner 2 pesos. Yo empiezo el procedimiento. No, eso aparte. Eso viene de recursos humanos. Porque si todo viniera de mí y ellos tuvieran un cariño, no importa, porque cuando quiero mandar 20
cuando es un donativo acá, tengo que ir al profesor que se, porque la verdad no funciona bien,
Pero no para los 3.000 pesos. Eso técnicamente es un donativo, eso técnicamente es un proyecto. Bueno, nosotros podemos hacer donativos. Porque nosotros no, el problema de nosotros no es la definición de lo que podemos hacer, porque nosotros tenemos dos potes de dinero. No, pero es más complicado todavía, porque Lincoln tiene dos potes de dinero. En términos generales, tiene un pote que es lo que viene del gobierno, que tiene 8 millones de pesos, y es un montón, es todo el dinero de Lincoln, el 99% del dinero. Y tiene el dinero que de alguna forma Lincoln produce. La dividiría, vending machines, la propiedad intelectual que a través de los años. Todo eso no entra en el pote de dinero, pero como no entra en el pote de dinero y es irrestricto, todo el mundo quiere esos chavos porque no tiene que estar pasando. Entonces, además de que lo razonable es si tú quieres hacer algo que está haciendo un proyecto que sea 50 centavos, pues tengo que cargar sobre el proyecto, no se lo puedo cargar al otro pote de chavo. Ahí es que entra la complicación. Tengo que justificar, tengo que hacer sourcing, tengo que hacer un statement of work, pero yo puedo hacer todo eso. O sea, yo te puedo hacer un ghostwrite del statement of work y enviarlo si tú me lo envías. ¿Entiendes? En el letter de la universidad. O alguien me lo envía. Whatever. Eso es fantástico. Lo pongo en el proceso y ya. Al principio se va a tardar el tiempo. Y lo otro, te lo digo porque yo hago esto 10 veces al año con 10 universidades.
Mira,
Genérica,
pero la bota ya la pierde.
lo que se llama son no, esta noche no puedo, tengo que arrancar pasado. Tú conoces a John Rivera, ¿verdad? Tú no conoces a John Rivera. Tú conoces a John Rivera. No, porque se grabó el japonés. Yo con nosotros al principio y después yo estoy aquí en los 90. El trabajo es de allá en la hija se casa mañana. El sábado y estoy en el corrido de que mañana tengo que salir corriendo para irme temprano mañana. ¿Verdad? No, pero yo estoy ahí. Yo mañana. Exacto, pero yo viajo mañana para el lago de sábado. Pero anyway, a lo que iba era que la va a tener que estar seguro que hay dos cosas que hay que generar. Una carta de yo tengo 1000 copias por ahí, una copita que les va a decir algo como que sí, este proyecto, no, lo estamos con él, whatever. Es una especie de carta de apoyo. Para yo mandar chavo de proyecto, tengo que pasar por ese sonsor. Esa es la solución, pero yo lo mando. Te puedo averiguar un productor. Javi, mira lo que vamos a hacer. Déjame intentarlo en la lista de cosas para hacer. No, yo lo sé. Pero déjame. No, y tú dices eso y parece una sencillez, pero donde cuesta el tranque es que los mismos tipos van a trabajar probablemente entonces va a tener que haber una forma de componer que entre los artistas no se represente mucho el proyecto original. Si llega a eso, que lo dudo. Pero déjame apuntar esto. Dale. Nada, yo voy a apuntar esto aquí y yo te escribo después y cuadramos. Vamos allá.
Quedan 2 minutos para empezar. Hello? Good afternoon, everybody. Welcome back. Our next presentation will be design and implementation of a EV inspection robot. Hello. I need to control the volume over there because the batteries are new.
Hello? ¿Todavía no?
Todavía. No.
Cuando dejes el micrófono apunta. Y cuando estén parados hablando, no tapas. Que lo voy a tapar.
Tú tienes el espectáculo. Mira, también. No es tan solo con estudiantes, es también con profesores.
El PhD factor no te funciona.
No.
Los profesores es peor. Porque los profesores no siguen instrucciones.
Probando. No, está prendido. No se escucha, es un simple switch. Ah, ya está el negation field del profesor. Ahora lo dañé yo, ¿ves? Ahora ya. Hello. 1, 2, 3. Dice que tiene batería y todo. Lo bajaste mucho. 1, 2, 3. 1, 2, 3. Ahora. 1, 2, 3. 1, 2, 3. Hablar alto. 1, 2, 3.
¿Hay alguien que hable bajito? Todo el mundo habla ahí.
1, 2, 3. Bueno, espérate, Raúl es el que decide. Raúl, ¿qué hacemos? No, pero acá soy el ruido. Tiene como efecto especial de la voz de Chuy. Estamos IAP y sus bookies. ¿No tienes otro micrófono? No. 1, 2, 3. 1, 2, 3. ¿No se puede cambiar el canal? 1, 2, 3. 1, 2, 3. 1, 2, 3. Hello. Hello. A cero que es la batería. Hello. ¿Se escucha bien ahí? Pero mira. 1, 2, 3. 1, 2, 3. 1, 2, 3. Hello. No. No puede estar lejos. Como si las baterías estuvieran mal. 1, 2, 3. Tiene todas las barras. 1, 2, 3. Se oye un poco mejor ahora. Mira a ver.
¿Se escucha? Bien, mejor.
Tienes que hablar fuerte tú también.
Okay. Well, vamos ya. So, good afternoon. My name is Alanis. These are my teammates, Yadiel, Carlos, Fernando, Sebastián, Emmanuel, Ian, y Andel. We're going to be presenting the design and implementation of the PV inspection robot. So, as the use of solar panels exponentially increases in the renewable energy industry, the need for specialized processes such as the inspections and maintenance of said solar arrays arises. So to solve this problem, we came up with cost-effective autonomous robot with several imaging technologies such as a high-quality camera and a thermal camera to identify hotspots in the PV arrays. Now I'll leave you with Yadel and the mechanical design.
Okay, so for the mechanical design, we have the early design process that the team presented last year and the prototype that they designed. Over here we have our current prototype that we're working on, which contains a LED screw and a linear line bearing for linear motion across the X and Y axis. We have the clamping mechanism that we designed, gears, and the wheels, the electrical component box, and the battery box. The skills developed as a mechanical division, we developed research skills because we needed to research the necessary components that were feasible for us. The design skills, we created and designed 3D models on Siemens NX that helped us create the real-life prototype. And manufacturing skills, we had the 3D printing, which we did almost all the parts, and we used power tools to help us develop those designs. Now I'll leave you with the design and electrical.
Yes, for the electrical components, first we have the Raspberry Pi 4, which is the mind of the robot. Then we have three stepper motors which controls and move the camera vertically and horizontally. We have the DC encoder motor, which moves all the robot across the solar array. And we have the DC stepper motor drivers, which control all the motors, and a DC-DC step-down buck converter. Also, we have the accelerometer, the time of flight sensor, and we have 6 limit switches at each corner. So when the camera touch it limit switch, the Raspberry Pi knows that that is the limit. It can move forward. And also we have the thermal camera.
Now, the next two slides are dedicated towards the power. And here we talk about battery sizing. Battery sizing is essentially the calculations behind the decision making of what battery we need and the capacity that it needs so that the system works efficiently for the tasks that we want them to do. For this analysis, we calculate the total current for all the motors, which are 2 DC motors and 3 steppers. Now you can ask yourself, why aren't the sensors taken into consideration when doing these calculations? Well, essentially, it's because we have another battery. It's the battery for the Raspberry Pi, which powers the Raspberry Pi and the sensors. Now, we use those batteries for the sensor because the sensors usually use a very small current. And in the other hand, we have the motors, which are 2 DC and 3 steppers, which usually take a larger value of current. Then we calculate the current. We are left with 7.4 amps, and then we add a 25% for safety, leaving us with 9.6 amps, which gives us approximately an hour for the system to work efficiently.
This is a power block diagram where we can see a schematic from the circuit where we can see the power, the battery that goes to a distribution board, that goes to a DC buck converter, 2 DC buck converters, and goes to the motor drivers that goes to the DC motors. Then the other buck converters go to a DC board that go to 2 motor drivers that power the 3 steppers. Then that data from the motors and the steppers goes to the Raspberry Pi, and the Raspberry Pi is powered by the Pi sugar battery, and the Pi sugar battery powers the sensors. So everything moves in that diagram.
Now for the Fritzing diagram. Fritzing is a simulator program. The difference between these programs is that Fritzing, you can actually see the circuit. You can actually see it. To create the Fritzing diagram, we had to learn how to use this program. We had to do the research of all the components necessary as well as its pinouts. And very important, we had to search the pinouts for the Raspberry Pi and its functions. In this case, we are using the Raspberry Pi 4 Model B. And of course, we have to test the components to make sure that the connections were in the right place. From the power block diagram that was explained before, we made the circuit in the Fritzing program. We can see the battery, and in this DC buck converter that moved to this DC stepper motor controllers that control the stepper motor drivers. That one is in 3 volts. The other one is in 6 volts. It's this DC stepper motor controller that controls the 2 DC motor with encoder. And as explained before, the Raspberry Pi battery is the one that controls the sensors only.
Now we're going to the software approach. We're going to start with a flowchart. First, we start defining the motor keys and the I2C devices, in this case, all the motors, the steppers, and the DCs. We start with the counter step, that is the encoders to know the position of the motor of the robot. So in this case, we start moving the steppers to the origin position if not set correctly. And then we're going to start the main process. In this case, we start moving the robot. We go to a third part of the robot. That is the if statement that we have right there. That's doing a while loop. And once it finds that place, it's going to start scanning with the thermal camera and taking the photos. Once it finds the edge, the corner edge is going to start moving horizontally, and it's going to start doing the process again until it find the edge. So, and it's going to end the process.
Okay, so for the implementation part of the project, here we have the images of what we managed to do. And that's the whole robot. The lower part we have right there. Down there is the battery, and those are the two buck converters with the two different voltages that go to the steppers that are on the other side. And the DC motors are inside of that box and inside of the other one in this exact same center. So essentially, now you will be able to see it working. So there's the horizontal movement of the robot across the array, well, across the solar panel in this case. And in the other, you can see the movement of the camera, which is the small little box that's going and stopping. That's when it takes its pictures, and then moves to the other row to take the other picture of the other cells. And now, work in progress.
The thermal camera implementation, where we use the FLIR radiometric lepton camera, and the work that we do with the camera is the pinout configuration, documentation about the component, Python code, and tools configuration, and the library about the camera that is PyLepton. The work that is still in progress is generate the main Python code for the thermal camera, and do more research about libraries, files, package, directory that need to be installed in the Raspberry Pi.
Okay, so for the computer vision part, we use we start with the library to say OpenCV. With OpenCV, we do all the image processing, and we use NumPy to store all the normalized data. We use the GPIO to control all the components, in this case, accelerometers and limit switch. We're also using the PyLapton, even though we are having problems because the library is a bit old, is 6 years old, and it received an update 1 year ago. So we're still having a bit of problems. We are thinking of using a C library for controlling the camera in this case. We use the Python programming language for the complete code base of the project and for serial communication. In this case, we also start doing the machine learning. In this case, we start researching this recently, so it's not completed, but we are progressing in that area. We start using TensorFlow and Keras and scikit-learn to split the data. We find a data set in Cable that have around 20,000 images that we are using for testing, and right now we have less than 30% in accuracy because we are early in doing the machine learning, so we're progressing in that area, and we have like a future goal that we want to increase the data set with our own image that we get from the robot.
So that's all. Thank you. Any questions?
A question, yes.
The solar panel used to make the experiment was like a very old solar panel, or was like brand new?
No, it was very, very old.
Very old.
Yeah.
Any other questions?
I have a question. in the lab, you will have a small array because you don't have the space to have a big array. But in the field, if you have like a big field, like in US, like you have like probably thousands of meters of solar panels. How you handle, how you place a robot? Because there will be this between panels will be a disruption. So do you have to create a new rail on top of the panels?
Well, depends on the array that you're using. So it really depends on the installation and the top ends can be adjustable. Sorry, the top ends and the top and the bottom end of the robot can be adjustable, such as the length of it. So that can be adjustable. So if the array of the solar panels is longer in terms of the amount it has, the robot can be adjustable, and the end it will have to be like also adjustable, but at the same time modular. So if you have this type of array, you will use like one end, and if you have this other type of array, you have another end.
Thank you.
Another question? Okay. If you detect like a defect in one of the solar panel, does the robot send a signal or something like that,
No.
or save an image and send it back later?
Okay, that is something that we're working on. We're going to implement a database. So in this case, every time that we take a photo, every run, we're going to send all the image to the server, and we are going to process all the image. And after that, we are going like to save the grid and the position that we take the photo. And for now, that is the plan that we have, like to see the places that are damaged.
Also, the reason behind that is because not only you can use it to inspect the solar panels, but if you have that database, you can also see the degradation of the solar panel if you do like interval inspections. So you will see how the hotspot will get bigger and bigger as the solar mother keeps degrading.
You said you have a 30% accuracy. You compare that to data like you analyze like the frame by frame, or it's just like how you what do you compare your data with?
Okay, in this case, the 20,000 image, we have, I don't know the quantity of how many good solar panels photos there are, but we have divided in good, we have a JSON file that have all the numbers of the image with the names, and if it says if the image is damaged, if it has hotspot, or all the kind of damage that a solar panel can have.
That means that you manually like check image by image.
No, in this case, by the data set that we have right now, we have all that data. So in this case, we are using that data to compare it with the image that we're taking, and we get the result with that.
¿Cierto? Cada dataset that is already labeled, correct?
Yeah. All the data set is labeled.
Es solamente perfecto, está bien.
Any other questions? Thank you then.
I have a question. Just in case you did your robot using 3D printers, which is very nice, but just in case that you will apply it in a real system, in a real farm, say in Guanica, for example, that is very hot, I think that 3D printer maybe will help your robot. So which modification do you think that you will need to do such that it will work under that environment? That at the end, that's what do you want? You use it for solar application, you use it for the sun. So which modification do you think that you will do? It maybe it will be more from the mechanical structure, but I would like to hear your answer.
Can I take the example you already did?
I wanted to hear the answer.
So the simple answer will be like it will be aluminum because it's lightweight, relatively lightweight, and resist high temperatures. And I already did a real life version of this robot that is like 8 foot by 4 foot in a actual array, and yeah, it works. It will need some other modifications because LED screws are normally that big, and they're not. So it will be useful if you found a LED screw that's 8 foot or 9 or 10 foot and wouldn't actually bend in the way of using it. Uh, but yeah, I think that will be some of the different type of structures, such as using aluminum, and in the case of its length, it will need to have a support in the middle. So at some point, we use the solar panel to grant that support.
Can you inspect during the night?
What?
Can you inspect the panel during the night?
Yeah, actually, if you want to do electroluminescence, it would benefit you doing it in the night because then you will actually be able to do that type of image in the night and the thermal one in the day.
I have a question, but it's for your advisor. Um, why aren't you using a drone?
And the reason is very simple. In this case, you wanted to use it for fixed places. For example, you are in Saudi Arabia. Those places they have a lot of solar farms, and maybe you wanted to keep it because unfortunately the drone you will have the problem of the air condition. You will have some weather condition that will affect. And in this case, you have a robot or a platform that always will be inspecting at any time. Actually, you can design those systems and you can do other modifications, like for example to clean, just to revise, to do different type of digital signal analysis or whatever. So that was the main reason that you wanted to use a robot of this type of structure instead of the drone, because maybe the weather conditions will not be good and you don't want to use it. And the other thing that is an advantage is that most of the solar panels, when you design a solar farm, will be the same type of solar panel. So you can use the same robotic system and will work, and you can use it for many functions. So that's another reason. And it is a low cost maintenance because you can create a platform for like to provide power to the drone, to charge the battery, and then to use it in that solar array.
Any other questions? Well, thank you then.
Our next presentation may be scary for some of you. The snake monitoring.
Yo no saqué foto de la serpiente porque no me atrevía ni siquiera a acercarme. No, ella le tiraba así.
They're so used to they probably grab them with their hands and put it in the neck. No,
no, no,
not yet.
Los otros días yo puse el café y me dicen, cuidado que ahí está la serpiente. Y yo, ¿qué?
Good afternoon. My name is Evan Jackson. I'm here with my friends and teammates. Orlando Saldaña. We are IJO, and we are very excited to present to you our project, Snake.io. So first off, what are we working with? So the U.S. Fish and Wildlife Service wants to eliminate the Puerto Rican boa from the endangered species list. However, biologists from across the island, including our client Dr. Puente from the biology department, think that there simply isn't enough data to make that action. Additional to that, getting that necessary data is an extremely difficult process. They have to manually go to caves, gather the snakes that they find, determine if they are tagged or not, and then get a rough estimate of how many snakes would actually live on that cave. This problem becomes a lot worse for extra inaccessible caves like the one we're targeting, which is in Agro del Camuy, which is a hike of 1 hour from the nearest road. Oh, my bad. So, what are we proposing to doing? Well, we call it Project Snake.io, and it's pretty much a long-term tag data collection monitoring system. So we have our power unit, which is composed of solar panels and big batteries, which will power the system for the duration. It's a minimum of 6 months just for them to go to the place again and get the data, but it's intended to run pretty much indefinitely. We have the transceiver unit, which is composed of antennas and readers, which will gather that tag ID as the snakes pass over them. And finally, our storage/control unit, which will gather all that data, format it, and output it on a CSV file for a client to gather. I'll pass it on to Orlando for a design of the hardware system.
Thank you, Ivan. So for hardware, we designed a 3-unit system. We firstly have the power management unit, which contains the solar panels for a total of 400 watts. Then we pass that power to the charge controller, which then charges the battery and powers the load when there is sunlight. And when there isn't sunlight, then we have the batteries as a backup for the system to continue during the duration of the deployment. Then we have our control unit, which contains a real-time clock and a removable flash storage that the client can use to collect the data. The reason that we need a real-time clock is because our client asked for a precision of where the records were made. So when the snakes were detected of 1 minute, and the clock that is contained in our single board computer, which is a Raspberry Pi 4, has an accuracy that is lower than that for the amount of time that the system would be deployed, which is 6 months. Then we have the transceiver unit, which contains the antennas and the RFID reader that we will be using to detect the tagged snakes. And in between the interfacing of the control unit and the transceiver unit, we have two multiplexers, which allow the control unit to talk to multiple readers using a total of 2 communication ports. Now we're going to talk a little bit about our enclosure design. We created a total of 2 enclosures for our antennas. Each enclosure contains a total of 4 antennas for a total detection radius of approximately 1 meter, which is the length of the cave entrance that we're targeting. We also have the transceiver unit enclosure, in which we have all of our readers and also our single board computer. So all the brains of the system are contained in a single box. And also we have an enclosure for our charge controller, which controls all the power from the solar panels and from the batteries to the load, and the solar panels, which needed to be angled for our location to get the best results in collecting that solar power. Now for our hardware considerations, since we are installing the system in a remote location, all materials need to be traveled with at hand. So transportability was very high on our list of considerations. We also have the isolation. The system will be alone for approximately 6 months. So if anything happens during this time, the system needs to be able to reboot itself or restart itself without the necessity of a human being on site. Also, we have our environmental hazards. We are working in a cave, so this is a very high temperature, high humidity environment. That means that whatever system we were to design needed to be able to withstand those temperatures and humidities. And as some of you may know, computers are not built for those kind of environments, so we needed to come up with a way to adapt our system to the cave environment. And we also have limited power. We are 1 hour away from the closest street. We don't have access to the grid. So we needed to come up with our own system for providing power for our system for 6 months. As for our hardware alternatives, as I already mentioned, we are using a Raspberry Pi 4 as our control unit. It has the interfaces necessary for our system, including USB interface, the UART communication ports, and GPI ports to control some of the integrated circuits that we're using. For our real-time clock, we're using a DS3231. The reason we picked this system is because it has a temperature-controlled crystal oscillator, which is important in our environment since this is a very high temperature environment, and for certain crystal oscillators that can cause it to drift. And since we're deploying for a very long amount of time, we need the system to be able to adjust itself so that the accuracy of the readings we're giving our client are not compromised. As for our power management, specifically our battery, we're using a lithium ferrite phosphate battery. It has a long lifetime, and most importantly, it requires no maintenance. So for our deployment of 6 months, we would not need to run any maintenance while it's running. And for the transceiver unit, we're using a very specific frequency. In our case, is for RFID, low frequency, which for animal tag identification, which is 134.2 kilohertz. This just means that it's very specific equipment, and since we're using a single board computer and creating our own system, we need to be able to interface with it. So we're using the Priority 1 Designs FDXB TTL RFID reader, which has a TTL interface which we can use, and is very low power and low cost. And now I'll leave you with Justin for our software design. With Ivan.
Thank you. So, as Orlando mentioned, we have our Raspberry Pi 4 as the brains of the computer, which will be interfacing with the transceiver unit, the RTC, and the removable flash storage, which will be used to store the data. And essentially what is happening behind the scenes is whenever, as Orlando mentioned, the system will automatically initialize itself if it happens to go through any power loss. So once it is up, it will automatically initialize all the readers and the antennas, and it will start data multiplexing through them. So once it detects a tag, it will store that tag in the current time, and then every 30 seconds, we will be storing all of that data formatted locally, and if there is a USB connected, it will add it to it. If there isn't, it will just keep storing the data locally until it finds one, so it can save that CSV file. And the programming language that we're using for this is Python. Not only does it have great integration with the RPI, and it's very easy to code and read, which is very important because this is the first of its kind, and we want it to be replicated across the island. But Python is a type of snake, so there was no way for us to not use it. I'll pass it on to Orlando again for the system schematics.
Okay, so now for schematics, I won't go very in detail about them, but as you can see, we have the solar panels connected directly to the charge controller. And that charge controller is both connected to our batteries and a DC to DC converter, which converts our 12 volts power supply from our charge controller and our batteries to the passive units. And for our control unit, we have the Raspberry Pi interfacing with the real-time clock through the I2C protocol. So we have an SDA and SDL line, and with our flash storage through a USB 2.0 interface. And for each of our transceiver units, we are using the Raspberry Pi to select which reader we are receiving information from and transmitting instructions to through a multiplexer and demultiplexer, and through 4 multiplexer and demultiplexer lines. And for each of those transceiver units, we have 4 antennas, each one connected to a single reader. So each antenna has its own reader, and we repeat that twice in order to obtain information about the directionality of the snake. That means if it's entering or leaving the cave, and all of that information is interfaced as previously shown with the multiplexer and demultiplexer to our control unit, specifically our Raspberry Pi. Now, actually, for our project status with Justin.
Thank you. Okay, so for our project status, as you can see, we were able to accomplish 100% of our project. It took upon 7.5 to 8 sprints, approximately. So yeah, going on into our results, these results itself were based on a cave we went yesterday to in Arecibo called Culebrones, where we actually put to a test our system itself with actual snakes, which you will see in a few minutes. But in this image itself, you can see our solar system and our preparation for it. And through this one, you can see our actual charge controller with our lithium-ion batteries, where they are enclosed so that they're protected for our actual habitat. The transceiver unit and antennas, which were explained previously. And finally, our control unit with the actual microprocessor and the USB. So in this image, you can see Dr. Alberto Puentes, who was holding the actual snake, which went through the constellation of antennas and was successfully detected. So for our future work, we actually forgot to add this, but we would like to alter our antenna systems so that we can actually get more range out of them for this low frequency. But due to low knowledge on this area specifically, we weren't able to actually create our own antennas. And we would also like to implement a UI system where we would have a database that would collect all the data from our actual transceiver unit, store it, transmit it to a cloud, and then show it up in a good looking dashboard where we would actually provide additional pictures of the snakes by adding a camera to our sensor system. So that would be all for our presentation. Feel free to ask any questions, and thank you.
Yeah. What limitations do you have that didn't allow to have a connection directly from the external, for example, to troubleshoot or to take the data from remote?
I can answer. I can answer that one. So essentially, it breaks down to first of all. Right. Sorry about that. So it boils down to the remoteness of the location. There is absolutely nothing except the cave on the location that we want to implement this. So the additional considerations that would need to be taken to make that approach were simply just too much work for the amount of budget and time that we were given to work on this. So, being the prototype that this is, all of the data will be stored, and on a future occasion in which you can access all of that system from a remote place, you just simply have to modify the code a bit, buy the antennas, and make sure to set up that GUI so it works just fine. But essentially it just boils down to the remoteness of the location and constraints of budget. Any other questions?
How did you estimate the amount of energy, the amount of power generation you will have with the solar panels, given that it's a very vegetated area because you are close to cave, and caves usually goes by there are always a lot of trees and vegetation.
Yeah, I guess it will.
So for those power calculations, what we did is that we take a very conservative estimate of the power that we will be needing and the power that we will be receiving from those solar panels. So we tried to go, I don't want to say overkill, but take a decent percentage of error to our calculations so that in the case that we don't receive as much power from the solar panels due to the high heat, which does affect the power that the solar panels can take from the sunlight, and as you mentioned, the vegetation that may obscure some of the solar panels, that our system can still function as intended. And of course, we took precautions in the case that our system does not run continuously and we lose power, that our system can reboot once it regains power. And for components such as the real-time clock, which needs to run continuously, it also has a backup battery that has a duration of way longer than our system would be without power, approximately like 10 years, due to the very small power consumption that integrated circuit would need to run just to keep up the time.
What challenges do you face in terms of reading the size of the entrance of the cave? Like as to implement this in another cave? Bigger or smaller cave?
Yeah, can I get it? Actually, our design was based on, as you said previously, 100 centimeters approximately. So for now, we wouldn't really be able to implement this into another cave. We went to another cave yesterday to actually test it, but the cave entrance was way bigger. So in that case, we would need to create an additional installation of additional antennas and most likely additional readers to our multiplexer. Any other questions?
Thank you all so much.
Thank you.
Thank you all. Our next presentation is design and implementation of a multiple single phase inverter. Is that the one? No? Single phase.
Yes.
Multiple single phase.
Just
With
single,
no more,
just a
without
single
more.
thing.
Okay, I got the title wrong. Okay, sorry about that. I saw that well, there were several single phase inverters. No?
Single phase. Error with the title. Error with the
Okay,
title.
okay. So,
Let's say they did the title there. Design of a single phase inverter.
there you go. So we are ready when you are. Just a reminder, the antenna of the microphone is over there at the end. The gray box over there that looks like a camera. If you point it down, it won't pick up as easy as if you point it that way. You're gonna start from both sides if you want.
Good afternoon. My name is Joselis Perez, and the SPI research team is going to present the design of a single-phase inverter. The team researchers are Alanis Colón, Valentina Ramírez, Alba Vega, Emil Fernández, Isabel Rivera, and Josh Lewis. The multiple single-phase inverter is with the band research project. It's a collaborative effort undertaken by a team of highly motivated and talented interdisciplinary female students from the University of Puerto Rico at Mayagüez. The team consists of 5 electrical engineering students and 1 mechanical engineering student. The primary objective is to design and construct a single-phase inverter and leverage this knowledge to develop grid-forming inverters in the future. The team is committed in pushing the boundaries of innovation and contributing to the development of sustainable and efficient power systems.
I will be explaining what an inverter is. An inverter is an electronic device that converts DC current power into direct current power into alternating current power. Its purpose is to provide alternating power that suits a broad range of applications. They're used in renewable energy and also as backup power for houses and businesses. In our project, we're using a single phase inverter. These have only one alternating current power output waveform as opposed to a 3-phase inverter that has 3 AC output waveforms. A deadband is a specific condition where the output voltage is there is no output voltage from the inverter. This is used to prevent switching losses, improve efficiency, and reduce harmonic distortion from the output waveform. A single-phase inverter with deadbands are used in renewable energy, motor controls, and uninterruptible power supplies. They are classified by their waveforms. Square waves have low quality power compared to the other two. These have rectangular pulses that have dead spots between positive half and negative half of the duty cycle.
I will be presenting the H-bridge design. The H-bridge design is a common configuration used in the construction of a single-phase inverter. It consists of 4 MOSFET transistors, which are arranged in a bridge fashion that allows to control the polarity and magnitude
of the output voltage. The logic of the MOSFET in the circuit is essential for our inverter to function. Each MOSFET turns on and off in a specific pattern, allowing the output voltage to vary in a sinusoidal waveform. The upper MOSFETs are turned on. That means a connection is made between the load and the power supply, allowing the current to flow in one direction. On the other hand, when the other two MOSFETs, the lower part of the MOSFETs, are on, this means that there is a connection made between the load and the ground, allowing the currents to flow in the opposite direction. Turning on and off these MOSFETs are done by the control signals, which are generated by a driver circuit. In addition to the logic of the MOSFETs, the H-bridge configuration also involves the use of blocking diodes in an anti-parallel with the MOSFET, which allows the current to flow in the load when the current in the MOSFETs is interrupted. The PWM signals, also known as a pulse width modulation. To control the transistors, a pulse width modulation signal is sent to the gate of opposite pairs in the transistors produced by the Arduino microcontroller. The use of a bootstrap is used to amplify this original PWM signal to ensure that the gate voltage is higher than the drain to source voltage. In the image below us, we can see a representation of what would be one of our pulses that represents the on time and the off time, which represents 50% of our duty cycle.
Now I will be presenting the bootstrap circuit. In an H-bridge, the low-side MOSFETs can easily switch because of the source pin is at ground potential. This allows the gate to be elevated to the specified 10-volt gate voltage. High-side MOSFETs are unable to access the common ground, and transformer primary winding makes the source pin begin to experience a rising potential, leaving the gate pin stalling. This is because the gate voltage is lower than that of the drain to source. The bootstrap circuit works such that the low side MOSFET is switched on. The supply voltage will charge the bootstrap capacitor through a diode and a resistor. When the low side MOSFET is switched off and the high side is on, the bootstrap capacitor discharges some of the stored voltage to the high side MOSFET to the gate pin. So our circuit parameters. The DC input voltage is 17 volts. The PWM signals are two. The first signal has a frequency of 60 Hertz, a output voltage of 5 volts, and a 0-degree phase shift. The second signal has a frequency of 60 Hertz, an output voltage of 5 volts, and a 30-degree phase shift. Our AC output voltage is 170 peak to peak and 120 root mean square. Our bootstrap parameters are the ones shown in the table. These were selected such that we would ensure that our gate voltage would be higher than that of the drain to source. The transformer is 1 to 10, its ratio, and our load is of 15 watts.
Okay, so for the switching part, this little bit of explanation. So most of you probably know that every periodic function can be described by a Fourier series, which essentially just breaks down any periodic function into simple sine and cosine summation. So why does this matter? So this is important because the inverter achieves its max efficiency when it's the closest to the pure sine wave. Therefore, there are a couple ways to get this. First one being using filters, and the one we opted for was to just simply shift the PWM signal by 30 degrees. So here's the general function diagram of our configuration, where we have the 4 MOSFETs with their alternate configuration for the switching, and we have the Arduino. It's 12 input for only power in the Arduino, which is going to give our PWM signals, and the 17-volt source for the MOSFETs. And in the load part, we have the transformer with 1 to 10 ratio connected to the load.
So, in the following slide, I will show the LT SPICE simulation that we used. We already discussed the parameters where we have our voltage source, then we have our bootstrap connected to our H-bridge configuration of our MOSFETs, the pulses that the Arduino will supply, and then the transformer with the 1 to 10 ratio that will be connected to our final load. Here we can see the circuit in LT SPICE completely built. We can see the V source, which is the source voltage. We can also see the H-bridge configuration of the MOSFETs, our bootstrap circuit, and our PWM signals, which were simulated in LT SPICE thanks to a command it has to create pulse signals. Here is a closer look to how we put the pulse signals. Both have an amplitude of 5 volts. One of them has a time delay of the 30-degree shift, basically converted to time by dividing the period by 12, and then you get the time of the delay of one from another. And then we have the parameters of the time that the semi-cycle will be on, and then the time of the whole period, and then the number of cycles that the simulation will run for. In our case, it was 5. Going back to our circuit, we can see our transformer, which is modeled by 2 inductors facing each other. One will represent the primary winding, and the other one will represent the secondary winding. In LT SPICE, you need to input a formula so it recognizes as a transformer. So that's what we did. And our secondary winding will be connected to the resistor, the 960 ohm resistor, which will simulate our 50-watt load. In continuation, once the circuit simulation was done, we started building our prototype, which is seen in the board. At first, we had a prototype that we had to use 4 boards to build, but we were able to optimize it to use half a board. And also, it is seen that it's connected to a transformer, the load. This transformer will convert it from 1 to 10 ratio, so we will get the 120 volts RMS in our output. And then something very curious, as you can see, there's a soldering iron as our load. Well, it has a temperature variation, so we were able to manually get the desired wattage that we wanted by varying the temperature. The resistance will be higher or lower. And then we have our final signals. The signal that is shown above is our PWM signal, and the signal shown below is our output signal. In both we can appreciate the deadband formation. The output signal graph suffers some distortions due to the voltage losses throughout the circuit. That is why the higher signal looks a little bit more square and perfect in comparison to the lower one. Something important to note here is that the purple or pink wave is the differential between the 2 measurements that were taken, the positive and the negative side, and then you get the actual dead band, which is the purple one. We can appreciate the first positive semi-cycle, then a period where it is 0, and then the negative semi-cycle. There we can conclude that we got the desired dead band wave output that we wanted.
Our future work entails outreach with our inverter demonstration, including an illustrative video showcasing the function of our circuit, of each element of our circuit and the interconnections in the inverter. The target audience is pre-university students with the intention of highlighting women in the engineering faculty. The results related to this work will be presented and published in the Unity Consortium on grid firming inverter with undergraduate students as co-authors for any publication related to a project. Thank you.
Any questions?
No questions? have an inductive load, if you change that to a capacitive load, will you change your design or not? If the load is not inductive, instead you have capacitive load, will that change your design or not?
Yeah, it's gonna change it because it's gonna rectify the design instead of making it a square wave. It would be a rectified wave, like as in a little bit of a peak upwards. So it will change the design per se.
Okay, so how you make it that it will be universal, that without knowing the load? Can you?
Yes. For now, that is part of our future work, which is something that we will be working on in the future, because the research for the microgrids, the main point is for them to be able to communicate the inverters one with another. So that is in our future progress that we will be working on next semesters.
What's the limit on the load that you can implement in that model today?
Yes, so we chose a 15-watt output, and the major limitation here was our transformer, which had a max of 3 amps. And to stay in a safe range, I think the max that we had with calculation with the highest peaks, you have to take your output current and multiply it by a 25% to get your worst case scenarios. So we played it safe, and the values were, I think, a 1.5 amps. So essentially, you could amp it up to the 3 amps of the transformer, so the wattage could be a little bit more. But we, to play it safe, we did that. And also for temperature reasons. Thank you so much.
Our next presentation is transformer sizing, design, and installation for a power hour in the loop simulation at one of our labs.
Good afternoon, everybody. My name is Javier Moscoso Cabrera. I'm here with Brian Diaz Aquino, sorry. And we're going to present here a process that we followed this semester to size a transformer, to design the whole process, and to install it, not ourselves, but with the electricians of the campus. As to give a bit of background to what we're doing, hardware in the loop simulations are basically the standard to set the standard on the most complex control, protection, and communication systems. Power hardware in the loop field provides the benefit of not just sending low voltage signals, but actually sending the actual power to the devices under test, which are inverters, which was mentioned here before. All of these are connected to a real-time simulator that has a power amplifier, and this permits for us to have the amplification of the signal that we want to address. You can, as a bit of context, we already know that DERs, distributed energy resources, are what everyone's talking about in Puerto Rico. It's because there's a need for it. You can see here that Puerto Rico has a lot of solar potential. You can see in the north, in the northern parts, there's a bit less, but in the southern parts, there's the most generation available. These are the connections of the actual power generation plants here. The red lines are the 230 kV lines, and the blue lines are the 115 kV lines. With power hardware in the loop simulations, we could literally simulate an entire microgrid for Puerto Rico as an example, but we could do simulations for microgrids in each municipality. As a bit of a background, additional background, this project involved basically putting to practice the knowledge that we learned from electrical machines class. Basically, to size a transformer, a delta Y transformer. In the delta side, it's 480, and in the Y side, it's 208 Y. Line to line, and line to neutral is 120. So these are the considerations that we need to take as of voltage of lines and currents of lines, and the same for phases with all of the specific connections.
So for our problem and hypothesis, today our university has the opportunity to become the leader on energy research. Thanks for the OPA-RT simulator that can simulate emulators, the R converters emulators, the R emulators by itself, and Greek loads emulators, and how my teammate said it can emulate the entire island. Our objective is to size and design and install a three-phase transformer so that we can use the OPA-RT simulator in the 222 on Stephanie laboratory of smart power electronics and aerospace.
As for the process that we need to follow, basically we work throughout the semester with electricians as to set or scan the site to see the conditions available for connections, to see the conditions in the breaker panel and the distribution board. Here are the calculations that we performed for the primary side and the secondary side. Primary being considered the 208 side, and the secondary being considered the load side. So we're expecting a current of 32 amps, and with the relationships that I presented earlier, we get these currents. And the sizing that we did for the transformer, we're talking about a 30 kVA transformer, so 30,000 volt amperes. As for to understand the transformer loading, or better, the capacity of what more could it grow in the future, we evaluated the currents that the currents that are expressed in the panel, and those were 14 amps and 20 amps. For those two cases, we calculated kVA for the 14 amps and for the 20 amps, and we added a 25% capacity just to be clear, and that led us to have a capacity of 48% at worst case scenario. Right now, running the OPAL in that transformer, we would be using, in a worst case scenario condition, 40% of it.
So here you can see a 2D model of the laboratory where we can see that the power lines that go to the transformer that's located here in a room inside the laboratory that then goes to the OPAL RT. And with this 3D model, it helps us organize better all the components and the new component that was the OPAL RT simulator. And the laboratory is with its divisions. Here on the back are the unmanned system. Here the 3D printing, the soldering station, the computers, and now the emulator side.
As for this design, this represents a one-line diagram of the installation. An emphasis on all of these designs were developed by us. So they weren't templates that we created the templates. This is the connection, right? This is the bus, 208 bus with a 10 gauge wire and a 30 amp three-phase circuit breaker. That feeds the primary side here considered as the 208 volts, right? The transformer is a 30 kVA with a 4.6% impedance. That's important for the protection calculations. In the delta side, we'd have no neutral. We have here a 10 10 gauge wire with a fuse disconnect box. This is the icon for that.
and this is another 10 gauge wire and the opal RC. These are the transformer parameters calculations that we presented earlier. And as for the results, here are the pictures of what all of this looks in real life. So talking about a 30 kVA transformer was a surprise for everyone because it weighed 355 pounds. That got to the lab, and that we were like surprised. But yeah, that's what got there, and it was a whole work to get it out of that enclosure. So yeah, that's the process of how basically we connected everything here. You can go to the 2D diagram of the right. Here's the MDP. MDP means main distribution panel. That's where the breakers are to feed everyone. So these lines, these green lines, are all the electrical addition. The blue square is the opal, as Brian said, but the connection goes from here. This is in the ceiling, by the way. From here, it goes down, goes here. This icon is the fuse disconnect, right? And this goes to the transformer, and then a hole is drilled in the wall, and then the transformer feeds the opal. And you're gonna see all of this physically here. And I just want to highlight that because we typically work with paper, but we don't typically work with actual stuff in real life. And having the physical implementation of these kinds of stuff is really enriching for students before graduation. So I just want to highlight that. This is the process of the electrician measuring the currents in each phase. They were not balanced. I'm not going to say the details, but they were not balanced. The ceiling, basically, he was taking the ceiling off because he needed to run the conduit for the cables. Here's the breaker panel, and all of these are existing. This is the new addition. It's a 3-pole breaker because it's a 3-phase circuit. This is the first day of installation, finished with this, and running the conduit through the ceiling and drilling a hole here, and then getting here with no connection here. This is the fuse disconnect. That had the handle. And this is the second day of implementation. The transformer is already installed, and here's the hole in the wall I mentioned, already installed permanently. And you can go to the next slide. And this is the hole, how it goes from the breaker from the fuse disconnect to the transformer, and then from the transformer directly to the opal. That's literally no one can take that off now. So yeah, that's the timeline for our project. Basically, we've been working since last year, but we were more focused this year. We did design, we did simulation, we did the installation. We were in the process of doing all the validation, and we wrote the IAP report, and here we are in the presentation. So
for future work, this project opens the door for more advanced research. Now with the advantages of emulating small communities, grids, and the whole island, as we said, this opens the new opportunities of research and new goals for our university.
It was mentioned, you can go to the earlier slide. It was mentioned also that the process that we're doing here, we could maybe publish a paper in the IEEE Frontiers in Education conference, because this is literally just putting what we learned in a class to practice. Like, I took the class last semester, so it's that kind of pace. And this opens, I want to highlight the opportunity that Puerto Rico has and the Colegio de Mayagüez has to be the leader in the whole Caribbean and Latin America in energy research. And with this kind of tools, we can be, we don't have to like have envidia anyone. So yeah. As for more of the future work, here's a physical representation or a conceptual representation of what a microgrid is. Basically, distributed energy resources connected to the same source, to the same load. The particular sizing, as I mentioned the transformer loading. It's 48% right now the capacity. So right now the transformer has space for another implementation of another thing to connect to it. So we could connect another simulator that doesn't need to be an op-amp. It could be an inverter, the inverters that they're developing. It could be grid forming inverters. It could be PV simulators like a Chroma. It could be a whole set of ideas. And we intend to explore those applications for grid forming inverters, microgrids, renewable energy, electric vehicles, and among other technologies. We want to acknowledge the help throughout the whole semester of Mr. Luis Cari Ayala and Mr. Javier Mari Bonilla. Cari is the director of electricians, and Javier is the electrician that you saw testing the currents. And yeah, that's all for us. Thank you, and we welcome questions.
Being here from Mayagüez, I know that typically the transformer on the main grid like breaks, sometimes one phase goes off. Did you on simulations evaluate what would have happened to the system if one of the phases went off and the other two keep like working?
Right now, we didn't do in-depth simulation of that because we don't have the software for it, or at least I don't have a software for it. But we intend to include that in future work because this is a work in progress of literally building a lab or rebuilding a lab that we're doing. So yeah, open to feedback, and we're literally as students as we go, and we keep learning. More questions? Well, that's it for us. Thank you. Have a nice afternoon.
I don't know how to pronounce the next word, but I will try. Ideolic? Okay, this is related to author personification.
Thank you very much. How's everyone doing? I know it's a fast presentation, so almost time. I hope this project is as interesting to you all as it is for me. We're going to be talking about author obfuscation and impersonation, aka idiotic transfer. So my name is Carlos Leiva, and my advisors were Kenneth, Pedro, and Trang. And special thanks to the IAP team for accommodating me last minute. So what idiotic transfer is, so this is in the domain of natural language processing, so AI. So how do we get an AI to talk like a specific human? So like everyone has their own style of speaking, of writing. How do we get an AI to generate text in that same manner? So before that, in AI, it's important to understand the problem that you're dealing with. In this case, we're dealing with idiolect. And I wanted to go more into the specifics of linguistics, as most approaches in NLP haven't done so. They've done more probabilistic approaches. So before that, I went to study on what an idiolect is. So using ontology techniques, I sort of identified features that are important that distinguish between different idiolects. And the ones that the proposed system can model is vocabulary, spelling, syntax, and grammar. So what I've done here is outlined a solution, a pipeline for a system that can do this, and I started working on a lot of the components.
So this is the pipeline I've outlined for doing such a task. So it starts off with we have two inputs. The semantic input is essentially what we're going to be paraphrasing to seem like it was written by someone else, and we're going to modify that text so that it seems like it was written by the author who wrote the impersonation style text. So let's say I have a sentence and I want that sentence to be paraphrased as if it were, let's say, a professor of mine. I would take the text I have from my professor and then input it into the system. And to do such a thing, so the system, we wanted to deal with cases when we have little amounts of data to be still accurate. So for that, I've incorporated another input, which is the author-separated data set. And what this does is we generate a model for the impersonation style input, so the utterances of the person that we want to impersonate, and we generate a model, and we do the same with the author-separated data set, which would generate a dialect model. In this case, we're calling it a knowledge graph. And so the dialect would be, let's say, if it would be a professor of mine, then the dialect would be Puerto Rican Spanish, which there's really no database that we have online for all of the utterances of Puerto Ricans have said. So what we do to improve on that is we pass it through a link predictor system. So we take the stuff that our professor has said and generate the idiolect, and then with the dialect, we input both of them to the link predictor, and that way we have an improved idiolect model. So it would have all of the features that we see in the input of the impersonation input, but also some predicted features that we get from the dialect as a whole. And then we generate the idiolect model, and then that only gives us the style of the person, right? But then we want to paraphrase some text to make it look like it was written by that person. So we have the semantic input, which we pass through a large language model and prompt it for paraphrasing. And each of those paraphrasing go through the same model construction, and then we compare the models of the idiolect versus the paraphrasings and score them. And what we do with those scores and rankings is we get the impersonation output, and then we use that output to fine-tune the large language model so that it eventually learns to speak as that person. So what we have here is a hybrid architecture. It's hybrid because we're using a model, which is a set of symbols and their relationships, but we're also using a predictor system, which is probabilistic. And the predictions that we're doing is from a top-down approach. So we're using a dialect, which is a higher level of abstraction, to make predictions on a lower level of abstraction, which would be the idiolect. And I see this being used for different applications also, not just dialects. And idiolect may be something more specific to a domain, like a technical domain. And this also could be used for fooling author detection models, so adversarial attacks, or maybe training other AIs to recognize if something was written by an AI or not. So this is a higher level overview of the architecture. We have the three inputs. Hopefully, if we're dealing within the same domain, then this only needs to be done once. What the model construction does is it tokenizes and parses the inputs, so essentially extracting the style, and generates the model. And then we have the dialect model, which is used to make predictions on the idiolect model, and that is used to score the paraphrasings. And then we go back to fine-tune. So an example of a case where we would want to use these predictions would be, let's say, we have an input from an author A, and he's British, and he writes flavor with the British spelling, so the OU, and then the paraphrasings generate two paraphrasings. So my favorite color is red with the American spelling, and my favorite color is red with the British spelling. If it's not implicit in the impersonation style output that he uses the word color with the British spelling, then the model might not correctly output that. So what we do is in the dialect model, we have the features that that occur together, most likely within other speakers inside of that dialect. And this is also done for style, so in terms of the parse trees, the syntactic structures of the sentences as well.
So yeah, this is the knowledge constructor. So this is how we, the knowledge graph constructor. This is how we generate the knowledge graph, and this is the calculation for the edges between the nodes. So the nodes are the tokens, and then the edges are the co-occurrences of those tokens for each author. And for this example, I've generated a model from 2 different authors as the dialect, which would be a news article written by a Puerto Rican author, and a YouTube video from a Puerto Rican speaker. And we also have the impersonation style output, which was an email from one of my professors. And then these are the graphs that we generate. So yeah, this is the 2 author dialect. The nodes are all of the tokens that appear in the dialect, and the color of the connections are the weights, so the amounts of co-occurrences between the tokens per author. And yeah. Also, the color of the tokens in this case would be the author that spoke that token the most. And then this is the idiotic model, so this would be what the email of my professor. Yeah, it's kind of cool. And then each of the nodes have their own embeddings. So right now there's systems like BERT, which they generate some embeddings. So you have the sentence input. In this case is the potion boiled over, which each token is represented by a 768 dimensional vector. And the way they calculate that is they have a token embedding which contains information on the semantics of the token, some segment embeddings, and then a positional embeddings. And this is important because the positional embeddings, they try to detect structure within the sentence, but they don't incorporate linguistic theories into understanding that structure. So really what they're just doing is identifying a linear structure, and what we studied in linguistics is that that's really not the case at all. So what I plan to do here is, right now I'm also working on another research group that is planning on outputting, so it's a parser that generates trees under a minimalist program, which is one of the new theories in, modern theories in linguistics. Each tree has its own interpretation. So there's not more than one tree per sentence, which means I can encode all of the terminals and non-terminals of the tree, use a pre-order traversal to convert the tree into a sequence, and then use the same equation that they're using here for the positional embedding, but use it for the sequence of that unique tree representation. And then what I can do is take the token embedding and concatenate to that the average of all of the tree vector, of all of the tree vectors in which that token appears. So that way we can encapsulate the average style representation that each token appears in per author. And then that would be what's encapsulated in each of the nodes. And then for the next part would be the scoring. So we first have to pre-process the paraphrasings. So we do the same thing, tokenize, parse, and vectorize the paraphrasings. And then we compute the node score and then the edge score, which essentially score on how similar they are in terms of style and occurrence of each token. We combine them and then we rank the paraphrasings. And then after, we also do a link prediction. So let's say, so the scoring only works for adjacent nodes. So what happens if we have a path where there's an intermediary node, we can't calculate a similarity between it. So there's several methods of solving that. The first thing is solving for paths where we have intermediary nodes. In that case, we can use a Jaccard coefficient and a cosine similarity because they exist in the same graph. But also we might want to add nodes that are in the dialect knowledge graph into the idiolect knowledge graph and try to predict where they would be connected inside the graph. And then for that, I would have to explore graph convolutional networks. And in terms of metrics, so what we want the system to do is to be able to handle cases where there's less data. So for that, we would use an F1 score where we have knowledge graph with link prediction and a smaller input, and a knowledge graph without link prediction and a larger output. So see if the graph with
with link prediction does as well as a graph without link prediction when there's a difference in data, a data size, so data poverty. And then after that, we would fine-tune a selected pre-trained model such as ChatGPT-4 or GPT-4 or Strap. Strap is used for paraphrasing, and we modify their loss function to incorporate the paraphrasing score and then train it on that. And then again, this is the pipeline. So we have the author-separated data set, the impersonation style input, the semantic input. So with semantic input, we generate paraphrasings, we construct the model, and then for the author-separated data set, we generate the dialect model. And then for the idiolect, we do the same thing. We improve on the idiolect model, and then we score the paraphrasing model with the idiolect model, see how well the paraphrasings are, and then we push it back to the large language model so that it trains on its own. And future work is to complete the end-to-end development. So right now, a lot of the pieces have been coded. Although the design has been changing a lot in terms of the semester, so a lot of the stuff that was previously detailed have changed, and I found better solutions. So right now is to integrate some of the older solutions with the newer and finish the end-to-end development. And so this is natural language processing, so we're dealing with semantics and syntax, but eventually we wanted to deal with phonological features. And the way I was thinking about designing the solution is that so it eventually could incorporate phonological features as part of the token embeddings. And yeah, then also explore different metrics for each of the parts of the pipeline, specifically rank-based metrics, which is what's used a lot in, let's say, like searches for YouTube or stuff like that. They use rank-based embeddings, and also expand on the idiolect ontology so that it can encapsulate more what its staff is, like with more features. And that's it. No questions?
What were some of the things that you implemented at the beginning that you decided that you were gonna be improving?
Yeah, so I use several different parsers. I use some of the NLTK libraries, and I ended up using, right now because the parser for Haskell is not done. So right now I probably use like 3 or 4 different parsers. Right now I'm using the Stanford dependency parser, which again doesn't encapsulate all the information. So I could have a sentence that has a representation, and then another sentence that has the same representation, but the interpretation of the sentences are still the same. So I was seeing how I could try to make it so that they're unique, and iterating over those solutions to make that happen is what has changed the most.
How did you compare because the dialect was changing on your output, how did you validate it that output was like like a proper representation of the person you're trying to impersonate?
Yeah, good question. So in ML, there's a concept, machine learning, there's a concept, garbage in, garbage out. So right now, that's a dummy, what we call a dummy knowledge graph, for purposes of visualization. But it depends on the use case of the idiolect. So if we're dealing with an idiolect of a person, and then we go through a different example, and then we also have an idiolect of the person that corresponds to the same dialect, we can use the same dialect model. And really, even if we have different dialects, we can still use the same dialect model. That's why they're separated into two things. And the dialect model wasn't changing, it was just the animation that was orbiting around so you could like visualize the words and tokens and how they're organized in clusters. Any other questions? Thank you so much.
Thank you. Okay, our last is a research. Our last presentation is our research sponsored by Verizon. Analysis of frequency antenna system across multiple spectrum bands.
So, no. Good afternoon, everyone, and welcome to this presentation. I'm very grateful to you all for taking the time to be here today. My name is Perla Thais Garcia Fernandez, and the topic of this presentation is analysis of frequency antenna systems across multiple spectrum bands. So the objective of this presentation is to focus on dealing with two main points. The first one is to analyze and compare the propagation of 28 gigahertz, 39 gigahertz, sub-3 and sub-6 gigahertz using a system to measure the power received in different locations. And the second one is to analyze the effects of radio propagation and wave field. Okay. And the second one is to analyze the effects of radio propagation and wave field in multiple spectrum bands to find a more efficient distribution and provide better 5G network coverage. So moving on to the introduction, I want to start by emphasizing the fact that antenna systems are fundamental for a user experience of the highest standard in wireless communication systems. And while these measurements ensure the distribution of the base stations to provide a better network accessibility and reliability, and therefore reduce expenses due to site deployments, get more satisfied customers, etc. But the most relevant to this project is that we propose to investigate the wave propagation to improve the system performance, 5G system operators, and other systems at lower bands. So let's continue with the methodology. The laboratory was carried out at different indoor and outdoor locations on campus. As you can see in this picture right here, shows the schematic of equipment of the process for acquiring the data. From one end, we place the signal generator. The signal passes through the power amplifier, and once it reaches the transmitting antenna, radiates the electromagnetic waves, and this is also called as propagation path. The electromagnetic waves are received by the another antenna and then is given to the spectrum analyzer. And this leads me directly to the next point, which is the equipment. As part of the system used, we have the standard gain horn with this frequency of range, the hyperlock with a frequency range from 680 megahertz to 18 gigahertz. It is important to highlight that this one is a locked periodical antenna, which means receive in only one direction, and the OmniLock with a frequency range from 300 megahertz to 8 gigahertz, and this one is an omnidirectional antenna, which means radiates in all directions. For all the tests, we use this amplifier, which has a ultra broad bandwidth from 2 to 50 gigahertz. And well, here we have some simulations of these simulations were carried out to make a design of the antenna in HFS. And as you can see, once it reaches the lowest point, it can be determined what the frequency is. In this case, it's 28 gigahertz. And the same for this example right here. Okay, so this is basically a visual representation of how or where we took the measurements. And this table right here has the total distance between the transmitting and the receiving antenna. And also you can see the displacement of the generator. And the reason why we took this into consideration is because in the analysis of results, we made a direct comparison between the path loss versus the distance, and also we took into consideration the displacement of the generator. Okay, so as you can see right here, shows the results, shows the graph for the frequencies of 3.7 gigahertz and 1.9 gigahertz. And for both cases, in the case of the 90 degrees, it can be seen that the greater the distance, there was an increase in the path loss. However, for the 45 and 135 degrees, in both cases, it can be seen certain alterations, and these can be caused by different factors such as the height of the walls or the region from the measurements, etc. And well, it is important to highlight that these results are without a displacement. So, for the results with a displacement, it can be seen that the greater the angle, there was more altered the expected results. And again, this can be caused by different factors such as the distance or the position. Okay, so here we have the data obtained for the higher and the lower bands, but taking into consideration only one point, which is the 90 degrees. So, okay. So, in the case of the 28 gigahertz, there was less path loss than for the 39 gigahertz. And in the lower bands, for the 1.9 gigahertz, there was more path loss than for the, there was, for the 28 gigahertz, there was more path loss than for the 39 gigahertz. This one is the higher bands. And in the case of the lower bands, for the 1.9 gigahertz, there was less path loss than for the 3.7 gigahertz. And well, so this can be caused because for the higher bands, they have a lower capacity to reach distances and cannot penetrate walls or objects well. And in the case of the lower bands, they have a longer range and can penetrate objects better. So, for conclusions, currently the results obtained consist in that the greater the frequency and the distance, there was an increase in the path loss. It is expected to continue completing the development of propagation measurement systems, including antennas and their support structure. And as part of our future, we hope to take measurements in completely open spaces and different environments to continue evaluating the behavior of the wave propagation. So, that's all, and thank you for your attention. So, if somebody have any questions? Thank you.
It was our last presentation. Thank you for coming. Don't forget, we have a dinner, and there's a surprise at 7 o'clock. Don't miss it. There's a surprise. You have to go and enjoy the evening. It's not only a supper. There's a surprise at 7 o'clock, sharp, in the Colegio Ingeniero. Does anybody need direction on how to get there? Not Google it, because have a good evening, and I'll see you soon.
Entiendo yo que para el segundo,
que es bien fácil. Esto, pues está bien. Pues déjame, y ya es oficial.
Sí, sí.
Ok, está bien. Pues déjame hablar con Kelly cuando vuelva.
Okay.
Si